This is our first video on static equilibrium. In mechanics, the two conditions for static equilibrium are that the sum of the forces has to equal zero and the sum of the torques has to equal zero. Another way to say that is that the net force has to be zero and the net torque has to be zero. Up until right about now, we've used this term equilibrium when we did Newton's laws problems, and it's meant that the sum of the forces had to be zero. Well, static equilibrium, when we're dealing with systems, means two things. The force has to all cancel, and the torques have to all cancel. And we're going to run into a few problems here where we show you, hey, is something in static equilibrium or is it not? For each case, we're going to find the net force on the object and the net torque about its center of mass, which is labeled with a dot. And we are assuming that we have a top-down overhead view. So there are no effects of weight or normal force. And then we're going to decide if each object is in equilibrium or not. Let's give this a go. The net force, 24 newtons, that way. Remember, this is not a pin here. This is just the center of mass. So the net force, 12 down, so 24. Again, we are above a tabletop. You can think of this as like a 2x4, a piece of wood that's just laying on the table, and we're up above it on the ceiling looking down. And there's a 12 Newton force here and 12 Newton force there. And what's going to happen with this 2x4? Well, it's going to start sliding. The net torque about the center is 0. 12 times 1 counterclockwise, 12 times 1 clockwise. So the net torque is 0. Is that in static equilibrium? It is not, because that 2x4, if that's what it is going to start accelerating across the table. Let's sneak over to this item right here. What's the net force on this one? I'm seeing 8 that way and 16 that way, so that's 24 newtons that way. And what's the net torque about this point? We've got 8 newtons times 1 meter, and that goes clockwise. That's in the clockwise sense, isn't it? And then we've got 16 newtons, and we've got 1 meter as a lever arm, and that's going this way. So that leaves us with a net of 8 Newton meters counterclockwise. This is definitely not in static equilibrium. The forces don't add up to 0, and the torques don't either. How about these last two cases? Let's look at the one on the left. What's the net force on this? I'm seeing 12, 12, and 24 in the other direction. 0 net force. Static equilibrium? Well, we don't know yet. We have to decide what the torques are. What about the torques about that point right there? This 24 Newton force, 0 torque about this point, because that line of action passes through the point about which we are taking torques. So we don't have to consider that. 12 times 1 clockwise, 12 times 1 counterclockwise. The net torque is 0. Let's put units on there just for fun. That thing is in static equilibrium. That thing is not going to start sliding anywhere, and it's not going to start rotating. It's just going to sit there. How about this last example? The net force, I'm seeing a total of 24 up and 24 down. The net force is 0. All right. Is that in static equilibrium? Well, we don't know until we check the torques. Let's check the torque about that point in the center. The 24 Newton force contributes 0 torque. Here we have 8 Newton meters in the clockwise direction, but 16 Newton meters in the counterclockwise direction. That's a net of 8 in the counterclockwise direction. This is not in static equilibrium. Now, what's going to happen with this thing? Well, it's not going to go anywhere because the net forces add up to 0, but it is going to start rotating. Its center of mass isn't going anywhere, but it's going to start rotating. If an object is in static equilibrium, as in this case on the left here. It's not going anywhere, and it's not rotating. And that's what we're going to need whenever we are solving beam problems, which we're going to do here in the next video.